All right, in this video, we're going to introduce double and half angle identities, and we're going to look at some problems using double angle identities. So the double angle identities are an extension of our angle sum identities for sine, cosine, and tangent that we looked at in the previous section. So in this case, when adding the two angles together, the angles would be equal. So for instance, a plus a gives us 2 times a. So sine of 2a is the sine of a plus a, which if we expand it out, we get the sine of the first times the cosine of the second, plus the sine of the second times the cosine of the first. So notice we have sine a cosine a that we're adding to itself, and when we add something to itself, we double it. So our sine of 2a is 2 times the sine of a times the cosine of a. And again, just an extension of using the angle sum in which the angles are equal. We have for cosine of 2a, cosine a minus sine a, which is cosine squared a minus sine squared a. And tangent of 2a would be the tangent of a plus the tangent of a, which is 2 tangent of a over 1 minus tangent of a times tangent of a is 1 minus tangent squared a. Now for cosine of 2a, there's a couple alternate forms based on this expression here. And if we recall from verifying trig identities, we had a couple alternate forms of the Pythagorean identity, cosine squared plus sine squared equals 1. So we'll be substituting some values in for each of these to come up with two other alternate forms of this cosine of 2a, which we're going to later see with the product of sum, or not the product of sum, the power reducing identities. So, for instance, if we look at the cosine squared of angle A, that's 1 minus sine squared A. This is an alternate form of the first Pythagorean identity. And then combining like terms, we get 1 minus 2 times sine squared A. Likewise, if we instead look at the sine squared A in our double angle cosine identity, that's 1 minus cosine squared. Don't forget to distribute this negative to the 1 and the negative cosine squared. We get negative 1 plus cosine squared, and then cosine squared plus cosine squared is 2 cosine squared. So another form of our double angle cosine identity is 2 times cosine squared minus 1. All right, so example 1, suppose the point P at negative 3, 4 lies on the terminal side of theta where theta is in standard position. So here's our sketch. And we're going to use Pythagorean theorem to get our value of r. And we got 3 squared plus 4 squared is r squared. Again, ignoring the negative here so we don't make any calculation errors by forgetting to put negative 3 inside parentheses first. And we get r equals 5. So with x is negative 3, y is 4, and r is 5, let's start with the cosine of 2 theta. Well, that's cosine squared theta minus sine squared theta. And cosine x over r, so we have negative 3/5. We're going to square that. Sine squared is y, or sine is y over r, so 4/5 squared. And when we calculate this, we get negative 7/25. Part B, find sine 2 theta. So sine 2 theta is 2 times the sine of theta times the cosine of theta. And we already wrote what sine and theta were, sine and cosine were in the last in part A. So using those same values, we get negative 24/25. Part C, which quadrant does 2 theta lie in? So here's our sketch again of the point negative 3, 4. And we know that it's theta itself is in quadrant 2. So if we double that, it's going to be, if we double the angle, we also have to double the endpoints here. So double 90 to get 180, double 180 to get 360. So if we double this angle measurement, it's going to be either in the 3rd quadrant or the 4th quadrant. Now to know which one it is, we have to look at our previous 2 answers and know which of those quadrants we have sine and cosine positive or negative in. So again, 2 theta actually should be in quadrant 3 or 4, not theta. 2 theta here. So from example 1a, cosine is negative and sine is negative as well. So out of quadrant 2 and quadrant 3, the one that has both sine and cosine negative is quadrant 3. So 2 theta is in quadrant 3. Again, this is a 2 theta here. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.